everybody. This is part of the Clojure Data Science Special, part of the Reclosure celebrations. And in this session, Oliver Mooney will talk about the language J. So Oliver, will you tell a bit about yourself, if you could?
Yeah, thanks, Daniel. So my name is Oliver Mooney. I'm a full-time software developer. I develop in a variety of languages. Clojure is one of them. Also things like TypeScript. Actually, these days mainly TypeScript, although I've done a lot of Clojure and ClojureScript work in the past, particularly around web development, as I know probably a lot of you have as well. And I've got a kind of a surface level or hobby level interest in data science. I've been taking a course online. It's using Python. I am not gelling with Python at all after using Clojure extensively. One of the interesting things about data science and Python is how they leverage dedicated libraries like NumPy. And that actually is what triggered me to look at array programming languages, of which J is one instance. You often see libraries like NumPy say they're inspired by APL and by J, and so part of me wondered, well, why not just learn these array programming languages directly to see what was the contribution, what was the appeal, and maybe that way I wouldn't have to deal with Python quite so often either. So that's what kind of sparked my interest. But I should say I'm very much in the early days of my journey into using J. And hopefully what I'm showing you today will reflect that. It will help see why it appeals to me. Hopefully it will appeal to some of you too. And also hopefully it will show what a nice complementary language J is to a language like Clojure as well. So can I share my screen, Daniel?
Yeah, that is wonderful. And yeah, I guess we could just begin.
Yeah, that sounds. Oh, wait, can I? Just one, yeah, okay, great. So hopefully you can see this title slide. Yeah, so array programming languages. I've got a couple of really high level slides here, and then I'm going to jump straight to the J REPL to show you what it's like to use in practice. So, but first of all, to answer the question about why J, J really reminds me of the Clojure maxim about things being simple and not easy. Simple means that you can understand them, you can understand everything the code is doing, but it doesn't take shortcuts based on you wanting to set up a big project really quickly without understanding what libraries you're pulling in, or any of those kind of practices that you often see in the JavaScript world or the EA6 world using React projects or whatever, stuff like that. And no disrespect to that approach either. That can be very effective when you need to get something done quickly. But if you want to understand your stack in its entirety or understand a computation in its entirety, J, like Clojure, is a great way to do that. J really, really focuses on notation. That second bullet point, notation, is a tool of thought. It's another, I think, exemplary value of J. There's a paper that Ken Albertson, the designer of the initial array programming language APL, he received a Turing Award for his work, and his acceptance speech was called Notation as the Tool of Thought. And he really shows how you can use a well-chosen set of primitives that combine nicely to express complex computations, both rigorously and quickly. Like there's a certain beauty that comes from brevity and precision that I think J exemplifies. Even though when you first see some J code, you might not agree with that at all. You might go, what on earth is this language? Because it does have that impact for a lot of people. It's very complementary to Clojure as well. As I was saying earlier, the value semantics are similar, and there's a part of J called forks, hooks, and conjunctions in general. That is a typo. They're very reminiscent of Clojure macros in terms of how they allow you to control your computation, how they allow you to redirect computations, to reorder it in time and in space. However, they do have very, very different target domains, which I think will become apparent. I won't talk about that too much here, but hopefully it will become apparent as we work through the code examples. Okay, so let's look at some code. Can everyone, by the way, hear me okay? I know because I'm Irish, I speak very, very quickly. So if I'm going too quickly in terms of speech, please just raise your hand and or give out, because I know I talk quite fast. So let's jump into the JREPL. I'll just close this and open a new one because it's full of my old stuff. So when you first install J, you'll go to the J programming language website, jsorter.com. You can go to get started, and it's very quick. You just press download and away you go. There's binaries available most likely for your platform, whether you're on Windows or Linux or Mac. And once you go through all that, you'll wind up with a set of icons on your desktop. So I'm going to click on this JQT 903 thing, which starts up the JREPL. This is using the Qt GUI libraries to be a cross-platform GUI REPL. They also have a command line REPL and a REPL available over a network server as well through the web if you want to do it that way either. But let's get started with some code, right? So I don't know about you, when you open up a new REPL in a new language, I always just try typing in random things to see what happens. So here is, for example, a number. What happens if you type in a number? Get the number back. That's probably a universal thing that you can do in Clojure, in Ruby, in Python, in J. It's kind of standard. And you can do the same with strings. You get a string back. Then you might try a basic computation. 1 + 1 = 2. 10 - 5 is 5. 5 - 10. Slightly weird, you get underbar 5. So Clojure, sorry, forgive me. Wow. J uses underbar to signify negative data, not minus. And that's one of the big things about J, the way it overloads symbols. It's very, very, very heavy on ASCII symbols, which I like. At the end of the day, I didn't think I would, but now I actually like it. So yeah, so other than that underbar 5, you might imagine that that's what you'd see in any initial REPL. Probably Lua will be the same, although I've never used it. So let's look at something a bit more complex. So J is an array language. Let's type in an array here. As you can see, there's no commas. It's basically an array is indicated by proximity separated by spaces. So that's 1 to 7. But of course, you don't have to type in arrays by hand. We can generate them. So let's generate an array. Okay, so that generated an array of integers from 0 to 9. So I guess you can tell from that that J's arrays are 0-based, not 1-based, which is the proper order of things. Then there's something else interesting here. That I dot is a single, what's called a verb in J. J uses a lot of similes around the pieces of language. So things like verbs, nouns, adverbs, conjunctions, they describe the entirety of what you might see in J. And in combination, those things are called phrases, and phrases form sentences. So they use structural names around English language pieces to try and inform you about how the language behaves. And that I dot 10 is a complete sentence. The I dot is called a verb, and the 10 is called a noun. Nouns are essentially data, and verbs are, they do the same, they take the same role as functions do in other programming languages, but they're not quite the same as functions, and sometimes the difference can trip you up. But I'll get into that a bit more deeply shortly. But the other thing to say here is that a lot of languages, J associates right to left. So it starts at the right, finds the noun, and then works left, and it finds the verb. It applies the verb to the noun to give you the result. That I dot verb took one argument on its right-hand side. That means it is, in J's terminology, monadic. It's nothing really to do with what Haskell calls monads. It just means singular. It's like the traditional definition of monadic when it was first brought in. For that, I think one of Newton's contemporaries came up with the word monadic to mean something similar to atoms. It just means it takes a single value. And nouns can also be dyadic. So I'll show you a dyadic version of I dot. 6 I dot 8. And that gives us back 2. So what the dyadic form of I dot gives you is index of. It looks for the position of the value on the right in what you gave it on the left. You'll often see values on the right referred to as y and values on the left referred to as x. So obviously this is a very, very different way of structuring code than what Clojure gives you. You could argue that Clojure is entirely monadic from J's perspective. You get if you define a function in Clojure, you'd have, say, or to invoke a function, you might have plus 1, 2, 3, 4, 5. I know from Clojure's perspective, you could say that that plus function is getting 5 arguments, but in J's perspective, it's getting a single argument of one list containing 5 values. And I think that's actually valid at J code as well. But in J's case, monadic plus just means conjugate, and conjugate of positive numbers just returns that positive number. So let's dig into that a bit more deeply. If I add an array to an array, you get back an array. You don't need to tell J how to loop through the values to add them, so long as you observe some basic rules around the shapes of arrays. There's a lot to talk about there, which I'm not going to get into here, but it's very well explained in J's documentation. But in brief, you can use the shape of an array to combine using plus. So that will add 1 to every value in the array, or you could have, what else did I do? Okay, I'll dig into that a bit more. Does anybody want to ask me anything so far on what I've spoken about? Has this been too quick? Is it being okay?
Can I ask, what is the implementation of your arrays on the back end, or how did you implement them?
So I didn't actually write J, but the implementation is done with a dedicated C backend. J is about 30 years old. It's a very heavily optimized C backend, and then with some J verbs that implemented as well on top of that. I have a lot to say about the action and implementation in after the code demonstration, which is part of the appeal of J. But yeah, so this is it's a dedicated C backend, I suppose, in short.
May I ask more?
Oh yeah, please, yeah.
So the unique selling point for J seems to be that I can work with arrays in a fast way. So it is a syntax to manipulate arrays in a fast way.
That's definitely one of the main appeals of it, yeah. There's more to it in terms of how you can combine verbs and arrays, or verbs and nouns, I should say. But I'm going to cover a lot of ground on that too. So hopefully, please jump in if it doesn't answer your question. But hopefully the next few examples will show a lot more about that.
Okay, so it perhaps would make sense to have the language, the syntax of the language, and have the backend something like TechML dataset, for example.
You could do that, but it wouldn't be as performant.
It would not.
No, it wouldn't be. I don't know. Should I just go through these slides to talk about that, or will can I ask you to hang on to later those slides and we can talk about it in more detail then?
Of course.
Yeah. Are you sure? Thanks. So I do talk about that a great deal. So yeah. So where else? So that just shows a combination of the right to left execution, the dyadic addition, and the way it reshapes data to allow you to use combinators like plus, or sorry, verbs like plus to generate results. So let's talk about the shape verb. If I do shape I dot 10, it gives me back 10, which means it's the shape of 10 scalars. But you can also use a dyadic form of shape to reshape an array. So if I do 5 by 2 shape I dot 10, you get back 5 rows of 2 columns, which is nice. And then if I try to, okay, yeah, so I can pull that back. I'm going to surround it with brackets just to prioritize the computation, and then do the dyadic search for a value again here. Let's do a search for 2, 3, and it gives you back the position of 2, 3 in the array. So I'm just trying to show here that verbs and combinations of verbs scale very naturally to the depth of the array that you're operating on. You can control that as well. You don't have to do it that way, but often the natural way it integrates computation between verbs and arrays is exactly what you want. And if I was to search for something that wasn't actually in that array, it just gives you back 5 as the position of the end of the array, so it didn't actually find it. So yeah, that's verbs and nouns. Nouns for data, verbs always return data, but you can operate in verbs. So in a lot of the functional style programming you do in Clojure, where you map a function onto an array of data, you do a lot of computation that's similar in spirit, but different in specification. So I'm going to get a total of an array here, and it's 28. So that slash character here is what's called an adverb. Adverbs take a verb directly on the left and modify it to return a new verb. And what adverbs do is they tell verbs how to interact with data. So in this case, I'm sure you can see that this adverb is called insert. It's again monadic. It takes it returns a verb that takes a single value here, and inserts the plus verb in between each of the numbers to give you a result here, which is 28. But of course, you can also do a monadic form, or sorry, a dyadic form of that. So if I do take the first 7 integers, and then again on the right, you get back a table. And hopefully you can see this is the additions table from 0 to 6 and 0 to 6 across the top. And it just shows you, say, 6 plus 6 is 12. So there's a neat way that J has of extending verbs from monadic to a dyadic form. That it's a very, very compact way of representing computation, but it does give you like extraordinary ways of expressing computations that are very, very rich and very, very full, which I really enjoy. Let's talk about function definition next. Suppose you want to take this is kind of a famous example of J code. If you want to get the average of an array instead of the total. Actually, no, before I do that, I'll do another adverb to show you that you can nest adverbs. So here above we had, again, the total of an array. But if I modify that one with a new adverbs, again, adverbs take verbs and return new verbs, and execute that, hopefully you can see from the code here, this has actually generated a running total. So it's this monadic version of this adverb means prefix. So it takes the first version of, it takes a 1 and applies sum to 1 for the first answer. Then it takes sum, applies it to 1 and 2. Then it takes sum and applies it to 1 and 2 and 3. So basically takes the prefix of the noun passed in sequence and returns the values here. But hopefully you can see that we've got the running total along the bottom. And again, it's only 3 characters against an array. Very, very compact representation of how to express that computation. Probably the most compact representation of that running total computation that I can come up with without defining a custom function to encompass that. And one of the nice things about J is that you often see these kinds of 3 or 4 character trains, is what these combinations are called. And you kind of wonder, like, why bother putting that in a function, right? You could give it a function name, you could call it running total, but that is like 3 times as long or 4 times as long as the actual 3 character definition of the function. So in a way, it liberates you from having to name things, which I really like, because you know, there's a classic line about how naming things is one of the hardest problems in computer science, because you wind up having to name so many things and having to give them unique, distinct names that make sense in context to each other. Whereas in J and APL, it's not unique to J, but in most array programming languages, you don't have to. You can just express the computation right there and then. You can see it. That's a pattern that any experienced J programmer recognize, that you're summing the prefixes of a noun. And yeah, it's like a I think they call it an idiom, where you see a known set of verbs in combination and go, oh, that's doing a running total. So there's no need to name it. It's obvious. It's as obvious to a J programmer as 1 plus 1 would be addition to somebody who's just familiar with that set of verbs. But you can, of course, define functions in J. I'm going to do that now. If I define, say, explicit mean, I'm going to call it explicit mean for a reason, which will become apparent shortly. Let's call it, you open up a definition with two of these curly brackets. I'm going to do, what's the first bit? C4. So when I said earlier, the arguments that you get to a monad or to a dyad verb are called X and Y. Here you can refer to those directly without needing to define them because it's a convention. So sum is equal to the sum of Y. I mean, even now I'm just kind of reading this aloud as sum. Tally is equal to, this is the new verb that you haven't seen before. So my computer has just told me that you can now see my screen. Could you not see this before? You could, okay, phew. That would have been quite an unfortunate talk. Okay, great. So tally here, this verb basically counts the length of a noun. So that gets to count. And then of course the average is sum divided by tally. And a verb definition just returns the value of the last line of code. And that percentage sign is what J uses for division. It's reminiscent of the dot line dot symbol for division that you probably may have used in school, because as you can see, the slash symbol here has been used as an adverb. So that's sum. So now as far as explicit mean defined, so if I do explicit mean of 1, 2, 3, 4, 5, 6, 7, you get back 4, which is the average of that array. So that's that is maybe not that unusual way to define a function in other languages, but it's a very, very long-winded way to define that function in J. And what I'm proposing to do now is just try and compress it down to something much shorter. So let's do that. You could, for example, explicitly, if you knew the shape of your data in advance, you could do it like this. Of course, there'll be back 4 as well, basically adding up on the left, counting the length of it on the right, and then using the divide thing to divide the sum by the length. Or you can do a really, really nice, neat thing in J, which is just to do sum divided by tally of. So you've got this very, very neat capturing of the nature of that computation. This is what J called the conjunction. This is an implicit conjunction called a fork. A fork takes in 3 verbs and returns back a single verb that operates on, that can operate dyadically or monadically. In this case, the dyadic version wouldn't really do anything that was interesting. The monadic version is the average of the array that you supply it with. And again, it just captures the nature of that computation really, really neatly and succinctly. I know I'm running tight on time, so I'll just try and explain a bit more about that last computation. If I pull in this code, J comes with a lot of utilities to let you try and understand what your computation is doing, which is always useful. So if I put this in and this in, and then this is a dyadic hook. I did that properly. No, I didn't. Okay. Oh. What I'm doing here is loading a library called function display. I'm then going to try and tell it to display functions in using mask format. And then I'm going to tell it, I'm inventing 3 verbs called F, G, and H. I really, at times like this, miss my Clojure REPL and my Emacs integration, because it would be much, much quicker and easier to do this rather than you guys watching me copy and paste like an idiot over time. But okay, so that should be enough. And so if I grab this, yeah, so it translates this fork here, which you can see here, 3 verbs. There's the X and Y arguments. It translated into what you might do using maths. So as you can see here, it gets the F verb, takes X and Y as your arguments and applies it to, or F gets applied to that. Then it takes the H verb on the right-hand side, takes the X and Y arguments and applies them to that, and then gets those 2 results and applies G to it. So in the case of our hook above, G is divide, F is sum, and H is tally. So it basically helps you try and understand how the order execution and how it combined in what we displayed earlier. So hopefully, let's go back to the slides here. Hopefully that made some sense. So this is, for me, part of the real appeal of J, because it's done in C. You've got 3 main improvements to see. It's to CPU advances in speed. Recently, once we ran out of megahertz, we started doing things like instruction level parallelism in CPUs. That's things like hybrid threading. We've increased core counts for large grain parallelism, and we've used SIMD vector machines for small grain parallelism. So when I said earlier, you could use something like TechML to build an analog of J, you definitely could, but you would miss out on this. And this is a major reason why I'm interested in J, because you get to, it brings you closer to the underlying vector machine execution model that has been the case in most of our CPUs now for the past 20 years. They usually operate on 4 or 8 values at once. And when you're doing things like +1, 2 in Clojure, you're using the JVM's addition model to add individual integers. But the CPU itself is capable of adding 4 integers simultaneously or 8 integers simultaneously. And the JVM currently doesn't really allow you to express that kind of computation. There are some JEPs out there that are trying to bring SIMD style vector execution to the JVM, and they've been integrated into the versions 16 and 17 of the JDK. But they've only looked, I think, in the main at Intel SIMD, so things like AVX and SSE, which is most of our machines, so it's a good first choice. But I'm on an ARM machine, so it doesn't really help me. But the great thing about J is it's naturally amenable to this type of execution. Verbs are often naturally made parallel. There's no loops in them. They're not combined in a way that you have to run them in sequence. You can take them and run them in separate cores. And arrays themselves are the kind, especially small arrays, lend themselves very naturally to SIMD implementations. And J, because it's how it's written, can take sequences of verbs like the one I just showed you around getting the average, which was sum divided by tally. It can run that with a SIMD implementation, and it has a huge amount of these special combinations of these verbs to optimize that kind of computation. So if I look at this page, these are all tips on how you can use those. And I don't want to, obviously we haven't got time to go through it in detail, but it just gives you tips on how to evoke them, how to make sure that you're getting these AVX-based implementations rather than the sequential version that you would have to use otherwise. If it uses tricks like execution in place, if you don't see intermittent arrays, you don't need to record them independently of each other, so you can just write over them as you use them. And then there's many lists of, I think down here, yeah, of, there's a lot actually, of how they use the underlying vector machine to optimize, yeah, here we go, to optimize the implementation of verbs. So there's way too much to go into here in any detail, but it takes advantage of the underlying CPU in a way that a lot of other languages don't, or can't naturally lend themselves to. And I would love to see a TechML implementation of Clojure or library in Clojure that once the JEPs extending the Java virtual machine to use SIMD-based implementations are in place. That would be wonderful. But I think that's a couple of years away still. So I think that is largely it. There's other benefits too beyond the performance implementation. They have very, very focused matrix libraries that are that allow you to specify matrix algorithms very, very clearly and neatly. They have a much higher level of abstraction that you see how the algorithm is implemented in a very, very high level, and makes inspection and proving of correctness much more straightforward as well. And then finally, oh, that is finally, yeah, so that's the last slide. I think I'm just about on time too. So yeah, that was a bit of a whistle stop tour of Jay, but if you have any questions or if anything doesn't actually make any sense at all, please let me know.
Beautiful. Oliver, thank you so much. Yeah, kind of mind-blowing to think suddenly to think about syntax.
Yeah, it's
suddenly other forms of code.
I've often felt like somebody
yeah, so
just my skull and opening it up just to like make me think of things differently. It's yeah, and it is a very syntax heavy language, but the syntax is very logical and straightforward and minimal as well. Not minimal in the way that in Clojure you're working directly with the abstract syntax tree, but minimal in terms of how you can get a lot done with a very, very small set of conventions.
Yeah. Great. And by the way, later today, we will have a session about a few of the relevant data libraries, such as the TypeNext and XML dataset, where Chris will be there to comment briefly, at least, about the state of these. And maybe if you could be there, Oliver, it could be interesting to have, yeah, great. And yeah, so we have some time for discussion, and I see that Lukasz has a comment or question. Would you like to? Oh, I think we might not be able to hear. Maybe something on your side. Oh, I see you writing something. Yeah. Yeah. So Lukasz is writing a question or a comment, and in the meantime, maybe Mike will like to say something, and then we will go back to Lukasz.
Yes, thanks, Oliver, for your presentation. I've been interested in J on and off, mostly off lately for a while, but it's great to get reintroduced to the language. What materials are you using to learn right now? What are you looking at?
I am using this. I don't know if you can see that. It's J, the Natural Language for Analytical Computing by Norman Thompson. I learn better from books than I do from online resources, so I basically was looking around from a J book. There aren't that many, and this one is 20 years old. I don't know how good a choice it is, but it's very, very dense. But then again, most J documentation is quite dense, and it's a demanding language to learn. It's an interesting book because it presents things in a way that is quite different in order from how I presented it. But if you want to learn J, there are some good resources on the J website itself as well. There's one document called J for C programmers that's long but in depth, but it does try to use the experience you might have had with other programming languages to get you orientated quickly. And then there's a couple of other online books on there too, basically PDFs. If you need to print out, you can. There, or you can, I think you can order them from Lulu Books as well. There's not a great deal of. There are some videos actually online. If you search on J programming on YouTube, there's a couple of nice introductory videos as well that are much more higher level than what I did here. really wanted to give a sense of what it was like to work at REPL to learn J, but those are also good starting points too.
I've been one. Can you hear me now? I hope so. Ah, perfect. I've been wondering if there's stuff that we can steal from J. I think that's the standard Clojure mindset is, it's a nice language like Wolfram yesterday. And okay, how can we steal all of it and instead of using the language? But still, you said that J is giving you a lot of ways to inspect what the stuff is doing underneath. Like you showed, you can say, okay, I want to know what the 3-part operator is doing there. And then it gives you a hint for that. And apparently there's more of it. Is there anything we can like borrow, steal, and plunder from it?
Well, yeah, I mean, certainly conjunctions really remind me really strongly of macros. And one of the questions I asked Chris at the DTAP Next talk, one of them that we had during the week, there's a similarity conceptually, although not in practice, between transducers and some of the conjunctions that J has. There's I guess you could, well, certainly for the using a single data structure or multiple data structures, like you don't need to create intermediate data structures and using transducers to do calculations. So that's one thing that Clojure already has. It would be nice. There's a common Lisp implementation of APL, one of the predecessor languages to J, called April. And the author of April basically rewrote the entire set of APL verbs in Common Lisp. So you could pull in the very, very rich library that J gives you almost wholesale using that as a starting point. And you can probably get very far with that, actually. I don't know in terms of the efficiency, like obviously the SIMD stuff, you'd have to wait for the JVM to mature, or I guess the node implementation could offer that too. I'm not too sure actually what the story with AVX or SSE type SIMD on node is, but you could certainly take a lot of the language depth manipulation to help you express computations concisely really quickly, if that was something that appealed.
Thank you.
Yeah, Amal, would you like to comment?
Hey, morning or afternoon.
Hey.
Oliver, yeah, thanks for the presentation. It's great to see APL, the APL family of languages represented, and appreciate your quote from Arthur Whitney. Actually, for me, I came across Q and the commercial product KDB Plus that Arthur Whitney created in 2006 when I was working at Lehman Brothers, and that was like my first experience with like REPL oriented or like using a REPL to develop, and I just remember it being so much more fun than like the other integration Java code I was using. And just for, this is like an anecdote of how quickly you can develop things in something like Q or J. We had to build this product that was called Panorama, which would source, orders and interest lists and like portfolio data and spit out alerts, based off of like what the market was doing off of tick data. And after like developing all the side components, the core logic of the actual alerting logic was not done. And we had only about a month of runway to actually hit the go live date. I was just fascinated because like there were people around me using Q, and ironically enough, they were consultants from Ireland. So like, I was curious and they showed me how to use it, and I just like went off with it. And within a couple of weeks of like just working on it on my own time in the evenings, just because I was fascinated by it, I built all the alerts and then just presented it as like, here's what you're looking for to hit the deadline. let's just use this instead of like trying to implement all this in Java. And well, it's hard to argue against a working implementation.
Absolutely, yeah. Fantastic. I didn't even know
And then the one other thing I'd like to add is, at least with my experience with Q, it was fascinating because this in-memory database, you started off with atoms and lists, and then dictionaries, and then a list of dictionaries with the same keys was a table, and then you could go back and forth from table to like vector to individual atom, or back the other way, and it just made programming so much more fun. And it made sense to write the language and then write the database in that language, because there's like so much impedance mismatch with like SQL or databases when you're trying to work with data. So this was fantastic, and I guess that's all I have to say.
Yeah, I think that's very true, though, that it does spark the same kind of joy. Like there's a real kind of pleasure to using our languages that, yeah, it's so rewarding. I mean, I recommend exploring them just for that reason alone, just to see how well put together they are and how much you can get done and how intuitive they are once you get over the initial discordant kind of nature of the code.
The only other comment I got was when they saw the code was like, hey, this looks like line noise.
Yeah. Well, it does, right? Very effective line noise, yeah.
I have another stupid question. Could you tell a little bit about the libraries that are available when you do some work in J? Because that's, I think, quite important to know before one goes deeper into the language itself.
Yeah, I mean, probably the best place to look at that is actually the J site itself. There's a page on here that looks at libraries. And let me see, I just need to hide you guys for a second.
Yeah, by the way, while we're searching, I guess after that, Ian and Sami will have short comments, and then Oliver will conclude, and we'll go for a short break. Yeah.
Yeah, absolutely. So yeah, there's a wide variety of languages here. I don't want to go into too much detail, but there's a lot. There's an awful lot here. It's because J is so long-standing, it can be quite hard sometimes to get a handle on what libraries are available, where to get them from, and how to download them. But yeah, I would start on the J website and go from there.
Thank you.
Sure.
Wonderful. Ian, yeah.
Yes, a small practical question. How easy is it to get this to play nicely with other things? Like how can you easily build an executable which you can then call from a shell script and pipe into something else?
Yeah, it's very scriptable, and normally I think when you're distributing a J application, you normally ship a front end that talks to a J backend. So you send over strings and get back your response and display that. So I haven't done a huge amount of deployment, or sorry, forgive me, I haven't done any deployment of J yet. I'm still in the early honeymoon phase, but from what I understand, that's what's involved. It's very embeddable as a C program as well. So.
Fantastic. Sami?
Yeah, I'm not sure how much in scope of this discussion, but I was a little bit curious, not being very familiar with the APL family languages, why J and not some other dialect? Is there, what are the differences? What goes into the decision?
Well, for me, and this is obviously, it varies a lot by individual, right? A lot of people do default to APL instead of J. The dominant APL distribution right now is by a company called Dialog. It's freely available. You can download it and play with it, and it's a very nice implementation. They took a lot of learnings from J. J was written based on Dr. Iverson's experience with APL and changes he wanted to make, and they've since incorporated a lot of those learnings back into APL. It's a very nice implementation. So that's also good to use. It does use the APL characters, which are basically a set of sigils that you have to learn and associate. But that's probably no harder than me learning arbitrary ASCII symbols to mean whatever they mean in J2. But for me, J is open source. That really appeals to me. And I can go into the C source, I can see the SIMD implementation, I can try and get a handle on how it's done, I can see how to integrate with other libraries. So for me, that's what made me choose J over APL. But APL is a fine choice as well. There's also a new open source RA language called BQN by a former employee of Dialog, and that's also well worth looking at. It tries to reimagine what APL can be as well, so it's another interesting approach.
Wonderful. Oliver, do you wish to say anything to conclude this part?
No, just thanks for your attention, guys. I know it can be quite a departure compared to Clojure, and hopefully it whetted your appetites or gives you something interesting to think about or play with. I'd love to know if any of you do kind of get into it more, how you find it or how you get on with it.